This is a brief of the laboratory tree. It is about tension tests of steel and cast iron. The steel is a structural steel. It is a ductile material. Under the tension force, it can deform a lot. The cast iron is a kind of brittle material. Under the tension test, it's going to fail abruptly. So the learning objective of these two construction materials are: first, to understand the mechanical behavior and mechanical properties of the steel and cast iron subject to tension loading. What is the mechanical behavior? It is going to be elastic behavior and the plastic behavior. The steel gonna show you both elastic behavior and plastic behavior. And the cast iron going to show you only elastic behavior. What is the elastic behavior? The elastic behavior is the behavior of material when you pull it and it's elongated, for example, 5 millimeter, and then you release the force, the material will recover to the same original length. That is elastic behavior. And what about the plastic behavior? The plastic behavior, when you poke it, let's say for 10 millimeter, and then you release the force, it's recover for 5 millimeter, and it still have 5 millimeter permanent set. That is a kind of plastic behavior. So elastic behavior is behavior when you pull the structure to some elongation and then you release it, it's recover back. But the plastic behavior would. And what are the mechanical property? The mechanical property, the most important according to the Thai Industrial Standard or the TIS for the steel are: first, yielding stress; second, the ultimate stress; third, the modulus of elasticity; and the fourth, percent elongation. So this kind of thing you're going to understand because it related to the Thai Industrial Standard, or also related to some other standards such as the JIS, Japanese Industrial Standard, and the ASTM, American Society for Testing and Material Standard. And second, during the performing the test, because of the steel have two types of behaviors, so we are going to perform two types of tests. One is load controlling test, another is the displacement controlling test. The load controlling test is like this: when you do the test, one of your friend gonna read the force, another one gonna read the displacement, and the third gonna be take a note, and the fourth may be the one that apply the force, the loading into the specimen. So when the test controlled by the guys who read the force, that's we call the load controlling test. For example, when the load hit 10 kilonewton, he asks the displacement reading guy to read the dial gauge and take the note. Okay, when it go to 20 kilonewton, they ask again, read the displacement and take the note. 30 kilonewton, read the displacement, take the note. This is called the load controlling test. How about the displacement controlling test? During the guy apply the force, the guys who read the dial gauge will control the test. When the needle move to 10, they ask the guy to read the force and take the note. Move to 20. Ask the guy to read the force, take the note. Move to the 30. Ask the guy and take the note. That's called the displacement controlling test. What are different? Sorry, that is the displacement controlling test. What are the difference between load controlling test and displacement controlling test? The displacement controlling test is one of the better tests because it can test both linear and plastic behavior. But for the load controlling test, it is only good for the elastic behavior. Okay. Next, let's talking about the tension test. The tension test is used to determine the normal stress and normal strain relationship of a material. That is to determine the normal strain diagram of the material. And you may recall the normal stress. The normal stress is going to be the tension force divided by the cross-sectional area of the specimen. And the strain is going to be the elongation divided by the gauge length of the specimen, or the L sub O original length. So over here, let's show you the equation for determining the normal stress, and this one for the normal strain. This is sigma, this is epsilon, this is the applied force, this is the original cross-section area of the specimen, this is the elongation of the specimen, this is the original gauge length of the specimen. Okay, and then you may cut this steel to be the specimen, and you put it, okay, between the machine here, and then you may apply the force here, and the magnitude of the load are read from the force scale, and also the elongation of the specimen can read from the dial gauge. Okay, so this one determined from the start, this one determined from the start, and the force and the elongation determined during the test. Okay, if that's the case, let's see our testing machine that I also show you in the video clip. You're going to apply this torsion to pump the hydraulic oil into this hydraulic cylinder. When the oil into this hydraulic cylinder, this axis gonna move up. Okay, push this portion of the frame to move upward. Okay, and since the portion of this frame is fixed, this one is fixed. Okay, since this one, the yellow one, is fixed, that's mean this portion also fixed. Okay, and since this one is moving upward, that means this one also move upward, and then the specimen that you are putting, okay, in this specimen holder gonna be in tension, and the pressure from this pump will move into the loading scale. and the red noodle, sorry, the black needle going to move to show you the magnitude of the force. And usually it's gonna come with the red one, and then when it hit the maximum, the red needle gonna stay there, but the black needle gonna return back. Okay, so if the loading test, the one who read this scale gonna be the one who control the test, to ask your friend to determine the the elongation for the dial gauge. But in the opposite, for the displacement control, the one who read this dial gauge going to be the one who control the test. Okay, the specimen is like this. And when you get the specimen, you got to measure the diameter 1, 2, and 3. You're going to find the average diameter of this specimen. This specimen is the steel. Steel can look like this. Okay, and you use the vernier to determine the diameter of the specimen. Okay, and you must to read it 3 times. Okay, the gauge is here. And we also have the universal testing machine that's going to use to test another set of specimen. The first set of the specimen is a kind of round bar, but we like you to see the real deformed bar. And then we're going to have some specimen from the real reinforcing steel and put into this kind of universal testing machine. And in this machine, all the things will control by the computer, and you will get the testing results, okay, the force, the elongation, okay, from this computer, and then you copy in your thumb drive, and you may use your Microsoft Excel to calculate the stress and strain, plot the graph, and if it needed, you may copy the graph from that's Microsoft Excel into the graph sheet. Okay, we coming into the stress strain diagram, and everybody studying this already. Okay, and the scale, the first one that we have is the Love scale. The Love scale is the scale that cover the whole picture of the stress strain diagram from the start until the failure. However, the Love scale can tell us only some specific mechanical properties, such as the ultimate stress, that's going to be the top of this, the fracture stress, going to be this point, and the modulus of toughness, which is the whole area under stress strain diagram. But according to the Thai Industrial Standard, or MOGO, there are other mechanical properties that are important. One is the yielding stress. The second is the modulus of elasticity. This Love scale cannot tell us, so we need to draw another graph within a more detailed scale, because the first portion of the graph uses to determine the yielding stress and the modulus of elasticity is unclear to us. Okay, we scale it up by what ratio? By putting this, that means we scale it up by 0.1 divided by 0.001, which is 100 times. And then we get this first portion of the test into this more detailed scale, 100 times. And then you can determine the yielding. Okay, the yielding can be this value. We use the lower yielding to represent the yielding stress. Okay, however, the yielding strength you got to determine by the end of the yielding region. Okay, this is gonna be yielding strain. Okay, this is gonna be yielding stress. Okay, how about the modulus of elasticity? The modulus of elasticity is the slope, okay, in the elastic region of this graph. You determine this one, the E is going to be delta of the vertical axis, okay, and then divided by the delta, the difference of the strain. Okay, that's what we should know about the stress strain diagram. However, typical the structural steel have the model for its stress strain diagram. For this example, is for the ductile material. Is ductile material. Most of structural steel are ductile material. It can elongate a lot because it's failure. It also have the yielding. The first part of this graph is the elastic behavior. Okay, we show this. We have elastic behavior as I mentioned before. When you put specimen, if the specimen elongate for 5 millimeter and you release the force, it go back to the original length. And the plastic behavior, okay, when you pull the specimen and then it's elongate for 15 millimeter, okay, and then when you release the force, there are still 10 millimeter still there. That's 10 millimeter is called permanent set, and 5 meter that's called recovery steel. That is going to be like the plastic behavior. Most of the structural steel have elastic and plastic behavior. Okay, and for the first portion of the elastic behavior, there is a point called proportional limit. Okay, and this proportional limit is the last point that the relationship between stress and strain is linear. And between this, the behavior of the material called linear elastic. And then when you increase the stress a little bit, okay, the graph going to be curved and hit the point called elastic limit. That is the last point that the material has elastic behavior. Okay, and if you push more force, it will move to the region called yielding region. But the yielding region is mean the material hit the stress of yielding stress, and it has strain increase continuously without increase of the stress. What happened here is when you produce the steel is hot. It will form the steel by cooling itself, and the grain of the steel form. Okay, during this part, the grain of steel form randomly, and then when the stress acting on the strain to the limit of yielding strain, that's grain that's randomly arranged grain start to be rearranged itself to make it more compact, and at the end of yielding, okay, it's gonna take more stress, and then at the yielding, the grain of the strain are rearranged systematically, and then it can take the stress. That is going to be the next portion of the steel behavior. This one called strain hardening. Okay, oh sorry, the important one also right there is the yielding stress. It's called strain hardening. That means it has the strain here and then it start to harden again. Okay, however, the stress gonna be increased, okay, continuously, and then when it hit the ultimate stress is end the strain hardening region. And also, when it starts the strain hardening region, you may notice that the steel is starting to be naked or is necking. I will show the picture of necking later. Okay, and this is called the ultimate stress. And when it get necking, it reduce the cross section of the specimen, and then the graft gonna be reduced continuously and fail over here as the fracture stress. We call this portion is the necking. For the civil engineer, we use the sigma allow in the length of sigma sub y divided by factor of safety. Most of the time, our yielding stress divided by 2 is going to be around here. So actually, the behavior of the structure under the action of the normal force is linear elastic. It should be. I should note that to you guys. And so the people who design and build the structure and then the structure fail, that is untypical, because our engineering structure gonna work only in a small region of this stress strain diagram. Okay, and that is fracture stress. This is necking. Okay, let's start to see. Now, during the strain hardening is very small, but it's going to be large enough to see when it's reached the ultimate stress. Okay, this is the necking. Okay, and then the necking can do like this. When it's separate at the fracture stress, the specimen gonna fail like this. This is the failure of the ductile material. Okay, and if you have the test result, okay, again from the Thai Industrial Standard TS, you got to take what actually the yielding, and the first point is the proportional limit. This proportional limit you can determine by putting your ruler and draw the line across this. When the line separate, okay, separate from, sorry, that is no good. Line separate, got erase this. When line separate from the graph, it's going to be the straight line here. Okay, it's going to be the last point that stress strain has the linear behavior. Okay, you may take this one for 240. And the yielding, you have upper yielding and lower yielding. Practically, we use the lower yielding because the lower yielding represent the real value of the yielding. The upper yielding just hit one time and then gone. Okay, and then ultimate, that is also important. This is important during for the TAS. Okay, and you also need to read the proportional strain here and yielding strain. It should be noted that the yielding stress taking at the lower point at the start of this graph is maybe like about this point. Okay, but the yielding strain they measure at the end of the yielding region. So if you take the strength, if you take the yielding start of the yielding strength, maybe you may take it about this. That is going to be what, about 0.0015, and then you divide 0.015 with the end of the strength. So in the yielding region, the value of this is about 20 times. That's why engineer use the yielding stress as the strength of the material, as the maximum stress that material take. Because after the yielding, the structure gonna deform a lot, and then it cannot function as intended. Okay, that is the importance of the yielding stress. Also, why don't they use the proportional stress? They didn't use the proportional stress because the proportional stress is hard to define like this. You got to put the roller and draw the line and see the separate between the curve and the linear line from the ruler. Okay, and then the fracture strain. Okay, the ductile material. I mentioned about the Thai industrial standard or Japanese industrial standard. They require you to find the yielding stress from the graph, ultimate stress from the graph, and also modulus of elasticity from the stress strain diagram. But they require you one more thing about the percent elongation. The percent elongation they require us to determine because it's going to tell you that this material is a ductile material or brittle material. The ductile material is a material that can deform considerably before it's failed. It's such as the structural steel, and it can absorb large amount of energy, so it can use in the structure such as the guardrail of the bridge. Okay, the brittle material is the material have very small yielding and is fail and is also fail abruptly, such as the cast iron or the concrete. So we test the cast iron because the cast iron represents the brittle material, and we test the mild steel or structural steel to represent the ductile material. To classify it, we use the percent elongation. Before the start of the test, we'll measure the gauge length of the specimen. That's going to be the term L sub O. And when the structural fail breaking into two pieces, you got to lower down the specimen and connect the crack point into each other. Okay, and then you measure the L sub F. This is going to be L sub F. You put the L sub F into this equation, you got the percent elongation. The TAS specify the percent elongation of a structural steel is larger than 20%. That means during the failure, the original gauge length will increase by 20%. Okay, that means that's going to be fail at the L sub F of 1.2 times 50, and it's going to be about over here. It's going to be about 60 millimeter. That's quite a lot, right? Yeah, that shows how ductile this material is. And also, you may measure the percent area reduction. You get the original A from this. That means you're going to know A sub O and A sub O here. And when the structure fail, you measure the diameter here, and you can compute A sub F. So the percent reduction of area have the negative value. Most of the time, this is supposed to be 50 or 60% at least to be the ductile material. And some material won't have the yielding, such as aluminum alloy, and also the cast iron won't have it. If you determine the yielding point of this kind of material, such as high strength steel, aluminum alloy, you got to put into the 0.2% offset. 0.2% offset, 0.2, you divide it by 100 is percent. So you got it for 0.002. And then you draw the line parallel to the linear point. It's cut anywhere in the graph. Put the horizontal force. You get the yielding stress. Okay, and the material have behavior different. Some of the material have different behavior in tension and compression. For example, the cast iron, also the concrete. The cast iron is the steel that has high percent carbon. So the carbon is put into the material of the steel. So it's produce micro crack. When you pull it in tension, the micro crack open, and then it's open very quick. So that's cast iron gonna fail abruptly, immediately under the tension force. In the opposite direction, if you compress the cast iron, all the micro crack gonna clutch each other, and also due to the Poisson ratio, the material gonna bug out. Okay, bug out. What is bug out? Like this. It's going to have larger at the middle. So what? So the cast iron can take a lot of stress until it fail. That is important. That's why we use the cast iron to resist the compression. For example, we use the cast iron in the rail of the crane. Okay, since the rail of the crane receive the compression from the wheel of the crane. Okay, and you're supposed to use the material in the way that the material is good. At the failure, these two materials have different type of failure. For the steel when it fails, it have the necking. Okay, necking is due to the shear stress. The shear stress that is produced by the tensile stress cause the slipping of the grain of the steel. Okay, and it's going to be 45 degree with longitudinal axis or with the direction of the tensile stress. However, the cast iron has micro crack. Okay, when the micro crack separate, it's separated by the tensile stress, and then the grain of the steel will move apart and it fell abruptly. This is show you the example that we have for the necking. This is our real specimen, and you're going to enjoy it. Okay, when you test it, and the failure going to be something like this. Okay, and failure of different material. You may see the failure of the steel maybe like this. Okay, maybe like this. Sometimes the failure is not symmetry because you install the specimen incorrectly. So when the specimen fail, you guys need to write how it fail. Okay, it may fail like this, it may fail like this, or it may fail like B, C, D, E, or else. For the cast iron gonna fail like this. Okay, and you take a note the appearance, the cracking pattern, the phi and cos of the surface of the crack. You draw the picture, make it clear everything. Okay, we have load controlling test and displacement controlling test. Okay, the load controlling test is appropriate for only the linear elastic region. Because of what? Because you use the load to guide the test. When you do this, increase the force, you find the strain. Okay, you increase the stress, you find the strain, and during its linear, everything gonna go together. But when it get non-linear, okay, the proportion won't work. Okay, and then you're going to have the problem to determine the correct strain. And for the displacement controlling test, this test is good for all region because you use the displacement. The displacement has what's so called the measurement of any kind of stress correctly. Okay, and it's going to be one of the best one. And then in the laboratory report, you got to draw the testing specimen and tell what the picture of the testing machine is into this your report. However, this term I allow you to take the pictures and put it over here, and you put everything into the data sheet, okay, and put the failure of the specimen here. After that, you need to conclude what you obtained from the test, and then you like to explain your result. So this is the brief of the laboratory tree, and you may have information to answer the pre-quiz, and then you may receive another brief from TA about the testing procedure that's going to be run, and what you should beware and what you should take a note. Those kind of things will be in the laboratory. Okay, this is the end of the clips for the brief of the laboratory tree.